Two of these widths would get you there, but I start at 1, so it's 8/5, but how about if I write it like this? Just so I can really help you see that this is telling you where you started, right? 1, and then how many 4/5 to go over. Take that number, plug it into the function, and that'll give you your height. Make sense? What's wrong? Are y'all just tired? What's happening? One plus 2 times 4/5, and then times 4/5. We'll do one more. What would the area of the third rectangle be? I'll squeeze that one in right here.
F of 1 plus 3 times 4/5.
So that's still 4/5. This is f of 1 plus 3 of those 4/5. Man, it is really warm in here.
Times 4/5.
And now multiply that times that, and that'll give you your area. So my third area is f of 1 plus 3 times 4/5 times 4/5. And then I could do the fourth one and the fifth one, right? And when I'm done, add them up, right? Get that area plus that area plus that area plus the other two, and we'd be done. That's how I do it, yeah? That's for 5, though. You sure you don't have questions?
So if it had started, like, the boxing or whatever, if they had started, like, at a number 3, it would be 3 plus
Yeah.
4/5 or whatever?
Yeah, like if this had started at 3, and we measured that this had to still be 4 wide and 5 rectangles, then yes, it would be 3 plus 4/5. The next one would be 3 plus 2 4/5. Next one would be 3 plus 3 4/5, right? 3 times 4/5. I'm about to generalize it. I'm about to generalize this concept. I just wanted to start it with something that was a little more concrete. So we're okay with it? All right, so if I were to add those up, right? The true area of this, the true area, which I'll call A, would be approximately A1 plus A2 plus A3 plus A4 plus A5. If I could do those, right? Now, do we have another way of writing sums like that that's a little more efficient? Oh yeah, we do. We have this notation. Remember this sigma notation? Have you seen that before? Other than on someone's shirt. Okay, this is a notation we use for summations. It's the Greek capital letter S for sum. And here's the way it works. At the bottom, you put what we call our dummy variable, our index. I'm going to use the letter K. You can start it anywhere you want. I'm going to start it at 1. And here I'm going to stop that index at 5. And that's because I have 5 things, right? Starting at 1, ending at 5. And then I just put here A sub K. So what this notation means is this. I'm going to first start where? K being 1. And I'm going to look at this expression and replace K with 1. So what would I get? A sub 1. And because it's a sum, now I say plus. Now I increase the index from 1 up to 2. And I do it again. A sub 2. Since it's a sum, plus. And then I do it again. It goes up by 1, 3, plus. And I keep going. And when do I stop? When I stop right there at 5. Okay? So this is a condensed notation for that. Yeah? All right. Now, I think there's 2 ends there. There's a mathematician named Riemann who's very famous. In fact, there's a there's an open question in mathematics. It's one of those millennial million-dollar questions called the Riemann hypothesis. If somebody can prove it's true, you'll be an overnight millionaire, and you'll probably have a lot more fame than you ever wanted in your life. I know you probably don't believe that like mathematicians can become famous, but there are some very famous mathematicians. So, someone proves the Riemann hypothesis, you're going to be in business for the rest of your life. Same guy came up with this idea for finding areas under curves, and it's called Riemann Sum. So I'm going to help right now develop his idea. Here's what he basically did. Let's say you have a function. Let's just take one piece of a function. Let's let that be the function f. And let's say it starts here at a and it ends here at b. Riemann said, all right, I'd like to somehow come up with a way of representing the area under that curve. All right, so keep in mind, we want the area underneath here. I don't want to shade it because I'm about to draw some other stuff in there. Understand? So he said, I'm going to start drawing some rectangles in there. I could do 5, I could do 10, I could do 100, but ideally I'd like to put n rectangles in there. N. And let n be just some arbitrary number. The bigger n gets, the better my approximation gets, right? So let's imagine drawing n rectangles that all have the same width to them. So I would have maybe my first rectangle here. So I start at A, I go out a certain distance, I go up, and then from there I go over. There's my first rectangle. Then I jump again by the same amount, go up to the end, over, down. Jump by the same amount, up, over, and I keep doing this, right? All the way across. And I'll come up with my n rectangles. Right? So there's n rectangles in there. Let's try and come up with a formula for each of them. So here's my first rectangle. Here's my second rectangle. My third. How about this last one? It's my nth one, right? I know that's hard to see. Sorry, that's a subscript n. Can you tell me the formula, or let's draw the first rectangle. Tell me how wide this rectangle is. What is it? B minus a divided by n. Everyone needs to make sure they understand where that comes from. The distance from here to here is the difference between these two numbers, right? When it was 1 and 5, we said it was 4, because we took 5 and subtracted 1, got 4. So if this is a and this is b, to figure out the distance between here, it's b minus a. But we're going to take that distance and we're going to cut it into n rectangles, right? N equals segments. So I need to divide that distance by n. Does that make sense? So earlier it was 4/5. In general, it's b minus a over n. Now, how tall is this first piece? F, right? And then where do I start at? A, right? F of a plus, so I started A, but remember that first point I'm using, I have to jump one time, right? So I say A plus, how much is the jump? What was it before? 4/5. Wasn't it always the same as this width? Right? So it's going to be plus b minus a over n. That will take me to this right endpoint of this first rectangle. Does that make sense? I plug that into the function, that'll give me the height. Multiply times the width, and that gives me my area. So the area of this first rectangle is f of a plus b minus a over n times b minus a over n. Do you see the similarity between this and the previous formula? We had 1 plus 4/5 times 4/5. How about the second rectangle? This will still be b minus a over n, right? The width. This will be f of a plus, now how many jumps do we want? 2 jumps, so I'm going to go 2 times b minus a over n, right? So my second one a sub 2 would be f of a plus 2 times b minus a over n times b minus a over n again. And following this same format, we could get the third one, maybe without even drawing it, right? What would our third one be? Just this formula with a 3 changed, right? Do y'all see that's the only thing that's changing in the formula? The only thing that's changing in the formula, this is a 3, this was a 2, and really there's a what here? There really is a 1 right there, yeah? So can you tell me what the last triangle would be? We would have an nth one down here, wouldn't we? The last one, the last rectangle has an area. Its area should be f of a plus n b minus a over n's times b minus a over n. Yep. And that last endpoint, isn't that last endpoint just b? Let's see, does that work? If the n's cancel here, you'd be left with a plus b minus a, wouldn't you? And that's just b. So it actually is, that's going to work. Does that make sense? Is this not cool? I don't know. I think this is cool. All right, so Riemann said, all right, great. There is a formula that I can use to create the approximate area underneath that curve, but I've got to add up n things, right? The more n's, the better it is. So here's what Riemann did. He said, all right, my area is approximately a1 plus a2 plus all the way till I get to an, right? Now, that's just using the sigma notation, summation k equals 1 to where? Where do I stop? N this time of a sub k, right? But that is just, now watch what I do here. Notice everything in blue here, right? That's the only thing that changes in each of these formulas. It starts at 1, then 2, then 3, and it stops at n. Everything else is identical, yeah? So if I wrote this down, would it be correct? Is that not the same thing? Yeah. Right? Because when I let k be 1, that's a 1, it's the first one. When k is 2, it's the second one. K is 3, third one. When I get to n, I'll be at the last one, right? And that would be a pretty good approximation. I'd still have to add up n things. I can't get around that, right? And the bigger n is, the better the approximation. So Riemann said, well, wait, what would the true area be then? And I think we've already kind of concluded that the true area, the way we could get to it is by letting the number of rectangles go to infinity, right? And that's what it turns out to be, what we're going to do. And how do we do that? What do we use when we want things to go somewhere? We use limits, right? We use limits. So this right here is an approximation. That is an approximation to the area. Right? Approximation. The true area of this is the limit as n goes to infinity of this summation. It's just, hey, look, let that go to infinity. And what happens? Automatically, if n goes to infinity, what happens here? Remember, a and b are constants. If n goes to infinity, that gets smaller, right? So the width of your rectangles is starting to shrink, yes? And you're going to have more rectangles to have to add up, right? Each of your steps is getting smaller. So as you're moving from one to the next, that's getting smaller. But that's the idea, is that the true area would be what you get if you let that number go to infinity. Do you all agree with that? Do you understand it geometrically? Yeah? Okay. So you can go through now, in some calculus classes, they spend the next part of the lecture going through and actually computing by hand some Riemann sums. And they're kind of a pain, and they're very, very tedious. Very tedious. And we're not going to do that. What I'm going to take you to now, let's just put pause here, okay? Everyone remember this, we're going to come back to it. We know that this formula represents the true area. We're going to kind of fast forward in time now to what's called the evaluation theorem. And this is a result of what is called the fundamental theorem of calculus. There are certain theorems in certain subjects that are, well, how should I say it? Fundamental, right? There is a fundamental theorem of arithmetic. There is a fundamental theorem of algebra, and there is a fundamental theorem of calculus. And one of the results of the fundamental theorem of calculus is this evaluation theorem. And here's what it says. And look, theorems are things that have to be proved, and they have to be proved rigorously. Mathematicians, like at some point in my life, I had to prove the fundamental theorem of calculus. But I was a math major, so it was a course I had to take and had to prove it. And here, we're not going to prove it, all right? We're just going to reap the benefits of it. So here's what the theorem says. It says that if you are going to try and find the area below a curve, if you want that area, let's let this be the function little f. If you want this area, it's equal to capital F of B minus capital F of A. And this is like, people do that, like mind blown type thing. This is mind blown right here. This is saying that if you want to know the area below a curve, all you really need to know is what? The antiderivative, right? Capital F means the antiderivative. You just need to find the antiderivative, and once you find it, do what to it? Plug in B. What's B? This right endpoint. Just whatever that number is, plug it into the antiderivative. What is A? The left endpoint. Plug that into the antiderivative, subtract those two numbers, and that answer is the area. That is huge. All right? Again, I'm not going to prove why. It's beyond the scope of this class, in my opinion. Some calculus classes, they do go through the proof, but it's kind of like, in my opinion, even when I was a Cal 1 student, like I wasn't ready for the proof of this. Like it's just like, what's the point of showing you a proof when there's so much stuff in it that, I don't know. I don't know. I'm not like trying to cheat you out of anything here, but it's kind of like I start speaking like fluent German right now to you. Like maybe some of you speak fluent German, but most of you are not going to speak fluent German. I don't speak fluent German. But exactly. But in the math, it's like that. It's like a language too. And so I start doing proofs and logic, and would you even know if I proved it? Like, would you be satisfied? So we're just going to wave our hands at it. But this is a major result, right? All you need is the antiderivative, which is why we spent weeks trying to figure out how to figure out antiderivatives, right? Okay. I told you to put back burner something, right? I said that other equation for A with all that limit stuff, right? Let's write that up here too. So I'm going to rewrite this right now. What we're saying is this. A, Riemann said, is the limit as n goes to infinity of the summation k equals 1 to infinity of f of a plus k times b minus a over n times b minus a over n. But we just learned that that's just capital F of b minus capital F of a, right? That's what we just were told by a theorem, that all of this is equal to this. Yeah? So what's a better way that I could write this, that I can condense this notation down into a nicer, cleaner notation? Yeah, so here's where it comes from. We say, you see this sum right here? If it were just the sum, I would just use sigma, wouldn't I? Just use sigma. It's just